aided Arts and Science College, situated at Malappuram district in Kerala. We are conducting a lot of research. Recently, the Department of Physics has developed an infrared rays controlled automatic on-off switching technology. Based on this, we have started a startup company for the manufacturing of the various outdoor lights. And we have also developed in the lot of technical advancement in the useful for the agricultural field. That is, we extracted the melanin from the human hair, and our beloved principal, Dr. K. Aziz, he is the key motivator behind all these research and innovation. We are happy to say that we have got very good resource persons. Dr. Sudhindra Raiprol, Scientist G, UGCDE Consortium for Scientific Research, Mumbai. Dr. Shivani Sharma, National High Magnetic Field Laboratory, Florida State University, USA. Dr. Munish Reniyam from South Korea. Dr. Pradeep Reddy from Chennai. And from the participant side, it's a pleasure to share that we have 102 participants from different parts of the country and also from the abroad. Okay. My duty is to say welcome all the participants. First of all, I welcome Dr. Aziz K, the principal of the PSMA College, to this program. I welcome Mrs. Munira P.O., the HOD of the department. I welcome Dr. Sudhindra Raiprol, Scientist G, UGCDE Consortium for Scientific Research, Mumbai. After placing a request, he immediately accepted, and I had met him in a program conducted by IIC Bangalore in 2016. He had a lot of experience in the research in the particular field, and also he has conducted a numerous tutorial sessions from different parts of the country and abroad on the same topic. Then I welcome Dr. Sudhindra Raiprol for this program. Next, I welcome Dr. Shivani Sharma from the National High Magnetic Field Laboratory, USA, for her kind cooperation and readiness to present a session in this workshop. I welcome Dr. Munish Reniyam, research scholar, the Pukien University, South Korea. I welcome Dr. Pradeep Reddy. He is assistant professor, the WellTech Institute of Science and Technology, Chennai. I invite all of the faculties in the college, in the department, and the beloved participants from the different part of the globe. Okay, with this small introduction, without wasting much time, I invite the principal, Dr. Aziz sir, for inaugurating the function.
Okay, Rashid, audible?
Yes, sir, audible.
Okay. Good evening, all. Most respected resource person for today's webinar, Dr. Sudhindra Raiprol, Scientist, UGC, DAE Consortium for Scientific Research, Mumbai. Respected Head of the Department of Physics, Ms. Munira P.O., dear Dr. Rashid T.P., coordinator for the program, dear Director of Spark Institute of Advanced Science, other resource persons like Dr. Shivani Sharma, Dr. Munishwaran, Dr. Pradeep Reddy, and all participants joined here for this workshop. A splendid good evening to one and all. Really, we all are facing the problems of the pandemic. All academic activities, research activities, teaching, learning process, everything affected severely during the last 1.5 to 2 years. In this situation, we are trying to make the impossible things to be to possible things for the betterment of student community. As the principal of PSMO College, a college around 2,000 students are studying with 8 postgraduate departments and 10 undergraduate departments, plus 5 research centers. Everything is affected. In this occasion, we are trying our best to make available various programs in the form of workshops, seminars, etc. by utilizing online platform. I'm very happy to see that the Department of Physics, one of the old departments in our college, giving much importance to research-oriented teaching learning programs. Dr. Rashid already mentioned a few activities going on in our college coordinated by the physics department. I'm very happy to see that during the last 3rd week of June, the same team, the physics department, also CIAS, Spark Institute, jointly organized a 1-week training program on ChemDraw and ChemSketch software. Again, after nearly 1 month, only past, again the same team come forward with another hands-on training program on some other softwares like Fullprof, GSAS, and JANA. All these things will definitely help postgraduate students, research scholars, postdoctoral fellows, etc., etc. And also very happy to see that as research persons today, Dr. Sudhindra Raipal sir joined. Others will join in the coming days. Dr. Shivani Sharma, Dr. Munishwaran, Dr. Pradeep Reddy, and also Dr. Rashid T.P. from the PSMO College. All these things highlights the potential of a department and also the faculty members. I request all participants to make use this event in a better way in this pandemic time. I take this opportunity to congratulate the Department of Physics, especially Dr. Rashid T.P., for spending his valuable time in coordinating this type of programs. I also take this opportunity to thank Dr. Sudhindra Raipal sir for being with us in this program. With these words, with full of pleasure in my mind, I inaugurate this 8-day-long webinar series on software training. Thank you very much.
Okay, sir. Thank you very much for inaugurating the function. And Next, I invite the director of the Spark Institute to share a few words about this program and also to introduce the SIAS Research Forum to the participants. I invite the CEO of the Spark Institute of Science, Dr. Hijaz. Dr. Hijaz, please.
Dr. Rashid, thank you so much. Could you hear me?
Yes.
Okay. So I'll share my screen. I have a PPT to show about our organization.
Not yet.
Okay.
Hello.
Okay. I think it is coming.
Yeah.
Okay. I hope my PPT is visible now.
Yes. Yes.
Okay. Thanks. So yes. So regarding this 7 days hands-on training, I welcome all the participants and also resource persons. So we have communicated the softwares that you should download before the hands-on training already through emails. So if anybody of you didn't get our emails, please contact us. And regarding the PowderX software, we still have to get the password. So we have already sent an agreement letter to its author. So we need to get the password from the author directly. So we hope that we will get it by tomorrow. Anyway, today you do not have to use it. So please wait for till tomorrow evening. By the time we will send you the password for the PowderX software. And so anyway, so I will right now show you. I will just introduce about this Spark Institute of Advanced Science and SIAS Research Forum. So basically, we are a research forum. We work under the umbrella of Spark Institute of Advanced Science. We do both academic activities and also research-oriented training programs. So our academic activities, right now we have completed 3 academic courses. The first one was a coaching for the Airport Authority of India's Air Traffic Controller examination. And the second one was a coaching for Central University PG entrance examination for both for physics and chemistry. And right now we are planning another academic program, which is a coaching program for the KVPY fellowship exam. The exam is going to happen in 7th November, and we are planning to start our coaching program from 20th August onwards. So these are our academic programs. Now, as much as we are interested in academics, we are interested in research as well. We are a group of researchers across the globe. So if this chapter, the forum works like the forum gives membership to students and faculties, and we organize conferences and workshops. We also help our members in research projects and internship, and we do mentor them, and we collaborate with academic and industry partners. So basically, we collaborate with academic institutions and industry partners in their research activities, in their major research projects. And we also give our members an opportunity to collaborate with different organizations across the globe. So right now we are conducting different training programs, and this is the Rietveld Refinement program is our 3rd training program regarding research. The first one was the 7 days hands-on training on ChemDraw and ChemSketch software. So this happened barely 1 month ago, and regarding this, we had resource persons in this program. We had resource persons from Perkin-Elmer, USA. They are the owners of the ChemDraw software, and we also had people from. So maybe some of you missed this program, and you may wish to join us. You may wish to join this training program. So the recordings of these training programs are still available. So if anybody of you wish to see this, you can contact us through email. And our second program was a faculty development program on online chemistry teaching. So this just wind up 2 weeks before. So in that we have introduced different online chemistry teaching tools, including the Amrita virtual lab. So the Amrita virtual lab people came and they introduced their virtual lab settings. And there were sessions on Avogadro and different other computational chemistry softwares. So again, the recordings are available. So if you wish to watch them, you can contact us. And then right now we are on this hands-on training on Rietveld Refinement. So both the previous programs were very good. Our participants were really happy, and we expect the Rietveld Refinement program will do the same. And our upcoming programs, we have already 2 programs on the way. One is a 1-month Python coding program for beginners. So this will start from August 16th. So maybe some of you are interested to join the Python coding program. So this is for beginners. So if you are already very familiar with Python, then do not join this program. If you are completely blind, yes, this is the program for you. And we are going to conduct a hands-on training on DFT calculation using Gaussian software. This program will be starting maybe in the 1st or 2nd week of September. So we will definitely let you know by email when we start this. But the advertisement for the, so if you wish to join, you can contact us. And another programs are there is a 5-day hands-on training in Origin software. This will also happen in 2nd week of September. And there is a 7-day hands-on training on advanced molecular docking. So maybe this will be an interest of chemistry and biology people mainly. And yeah, for all the researchers, there will be a hands-on training session on EndNote and Mendeley. So these are reference management softwares. So I think our research community is lacking professionalism mainly in writing their papers and documents. So yeah, so I think this course is the need of the hour, and this will be coming in last week of September. And there will be a research training in genomics and a hands-on training on latex. So yeah, so as I have already mentioned, you can take a membership of our research forum. So once you take membership in our research forum, you have different you will have different benefits. So one of the benefit is, so right now we are collaborating with PSMO College for this program, and for our previous program also we were collaborating with PSMO College. For the upcoming Python coding program, we are collaborating with another institution in Tamil Nadu. So right now, what we are doing is we are giving this collaboration opportunity to our members. So if you are a faculty member of our forum, the upcoming programs can be conducted in collaboration with your institution, so that your institute can take the credit for the institute accreditation purpose, NAC accreditation, all those kinds of things. Okay, so that is one of the things if you're a faculty member. And another thing that there will be at least 20% reduction for all the faculty members on all of our upcoming programs. And also there will be some exclusive programs which will be completely free for faculty members. For example, the faculty development program on the online chemistry teaching tools, it was completely free for faculty members of CS Research Forum. Okay, so it means full membership. For taking a faculty membership or a full membership, you have to pay 2,000 rupees for 1 year subscription. This is for 1 year. And there is student membership as well. So student membership can be taken by any students who is an undergraduate or a postgraduate or a PhD student. They can take a student membership. Student membership cost is 500 rupees, just 500 rupees for 1 whole year. And they will get at least 10% reduction in all the upcoming research and training programs. And yeah, of course, they will also get some programs for completely free. And there is a junior student membership program. This is basically for school students. So there will be some programs for school students as well. They can take a membership by paying just 250 rupees for a year. And we also do publish our works. So right now, this is our first publication, our first book that we publish under the umbrella of SIAS Publishers. So the book title is Learn Chemistry Through Demonstration. So this was authored by Dr. Sabil M. Bashir. He is an assistant professor in Vellore Institute of Technology, Amaravati. So yeah, so we are going to launch 2 calls for book chapters in the near future. So maybe some of you are interested to join us in this venture. You can please you can email us regarding this. And yeah, so this is basically this is what we do. So I request all those participants here in this program, in this Rietveld Refinement program, I encourage everybody, I strongly recommend to take our membership so that you can be in touch with us. And we also provide them platforms to conduct courses as well. So if you are a member, you can suggest, yeah, everybody will be an expert in their own region. So you can explore your expertise. You can suggest different courses, and we will make the platform for you. So there are numerous opportunities with us. So I strongly recommend you all to join us. If you're a faculty, take a faculty membership. If you're a student, you can take a student membership. So that's it. So right now, I think our resource person is already here. He's waiting for us to start. So thank you so much, Dr. Rashid.
Yeah. Okay, just thank you very much. Next time, our resource person, Dr. Rietveld sir. He is working as a scientist G at the UGCDA Consortium for Scientific Research, Mumbai Center since 2006. He completed his PhD from Saurashtra University, Dashkote in 2003 and postdoctoral research from Tata Institute of Fundamental Research, Mumbai in 2005. He has received the prestigious Alexander von Humboldt Research Fellowship and worked as a research fellow at Institute for Unorganized and Analytic Team, University of Germany from 2005 to 2006. He was awarded in physics for young scientists for the year 2010. Award in solid-state physics symposium in 2011. He has more than 181 publications in the peer-reviewed international journals, and he has presented his research findings in several national and international conferences. Also, his research interests include experimental conventional matter physics, with a particular emphasis on understanding the correlation between the structure and physical properties. He has expertise in crystallographic and magnetic structure determination using X-ray and neutron power and refraction methods. He has expertise in magnetic, electrical, and thermal property studies of novel magnetic materials for identifying application potentials. He has delivered numerous tutorial and lectures on structural analysis, magnetic properties of novel materials, and neutron as a probe for understanding structure and magnetism of materials in low temperature and high magnetic field conditions. I invite Dr. Rietveld sir to start the session.
Thank you, Rashid. Thank you very much. Am I audible?
Yes, sir. Yes, audible.
Okay. Thank you very much, Rashid, and thank you to Dr. Aziz also, and all the members of CIAS and your department of physics at PSMO College.
Thank you, sir.
And it's a pleasure to be here and interact with the students. So yeah, I will start sharing my screen and maybe I can start from there. Okay.
Okay, fine.
Okay. So my screen is visible to you, right?
Yes, sir. Yes,
Okay.
visible.
Yeah. Right. So at the outset, I would like to thank you all again for giving me this opportunity to come and discuss Rietveld refinement method with you for crystallographic structures using powder X-ray diffraction data. So before I go into the details of that, like Dr. Just now the speaker before me introduced his institute. Let me give you a brief account of what we are. We are UGCD Consortium for Scientific Research, and we have our headquarters at Indore, but we have our centers in Bombay, Calcutta, Indore, as well as one node in Kolkata. So if you go to our website, you can find more about us and what the activities we do. Okay, so you can see that IUCDAF, earlier it was known as IUCDAF, now it is UGC's Consortium for Scientific Research, is basically created for providing the high-end research facilities, particularly of the DAE facilities like the synchrotron, the research reactor at BRC Bombay, and then cyclosynchrotron Calcutta, and accelerator at Kalpaka. So all these DAE mega facilities are available to university researchers for carrying out their research. And in addition to that, we have set up many state-of-the-art and high-end equipments for low-temperature physics. Most of us work on experimental condensed matter physics, and we have certain programs on radiation biology also, soft condensed matter also. So all these facilities, you can actually visit our centers, our site, and look at the facilities. And all these facilities are available to all the researchers, and they have to use this user portal, and they can write to us what experiments they want to use, which facility they want to use, and they can come visit our centers. In normal times, actually, you can come stay with us and do carry out your research and take the data with you. But in this Corona times, actually, since the visits are not possible, so you can actually send your samples and we can do these measurements. Agree that it is feasible and the instrument time is available, allocated to you. So all the facilities like magnetization, thermal transport, thin film deposition, thin film studies, reflectivity, and all suite of measurements which can be which is possible are available with us, is available, accessible to all the university researchers in India. And I would like that users who are actually at the beginning of their career or the young faculties to look at these portals and look at the opportunities which you have in carrying out the research and using these facilities. And most of the institutes, most of the universities are not able to either set up this low temperature, high magnetic field facilities, which is a very intensive job to do and very expensive also. So CSR has this mandate of providing these facilities to the university researchers, and I think it's a very excellent opportunity to come and use that. And for the young faculties, I would request them who is interested in condensed matter physics and utilization of our in-house and mega science facilities of DAE to visit this website at UGC portal and to look at the possibilities of collaborative research. These are the projects for 3 years with a possibility of funding for a project student who can be enrolled for a PhD. Right. So I would suggest all the young faculties to look at this portal and make use of these facilities. In order to increase awareness of these facilities and this program, right now we are conducting 5 awareness workshops which will start from August 2. And these are zone-wise. Actually, there are 5 awareness workshops which have been planned. And for southern states, there's one workshop being coordinated by Kalpakam Center. And you can write to the local host and register yourself. And you can attend these workshops on the 2nd. And our Bombay Center is arranging one workshop on 4th, which will be on the similar lines. And but this is mainly for the western region of the country. At this point, I would like to mention that all the facilities, all the activities which we do, like Dr. Rashid can vouch for that, whatever activities we do is free of cost to the Indian researchers and for students. In fact, we actually take care of all the expenses which are required to cover a workshop or to carry out any scientific experiments. Okay, so the main motivation is that we, as a consortium, are mandated to add values to the research of the community, of the students who are working in the field of our expertise. So with this, I would like to come back to the theme of our meeting today, that is Rietveld refinement method for crystallographic structures using powder X-ray diffraction data. So at the outset, Dr. Rashid gave me a mandate that you are free to choose your time and pace. So I thank him for that. And what I have done is that I have distributed the lecture in 3 parts. Instead of clubbing everything together in 1 hour, 2 hours, we can take it leisurely. We can go at our pace, and you can stop me at any time if you have any questions. So what I have planned is, so today we will go through some of the requirements which is needed for Rietveld refinement method. It's not just a program. Okay, it's a method which involves crystallography and some knowledge about the physics of the sample, physics and chemistry of the sample. So what we'll do is we'll go through some of the requirements of a powder diffraction data, particularly for X-ray case, and how we will see how your Rietveld refinement method will be useful. So it is more like a lecture today using this presentation. And tomorrow and day after tomorrow, I will demonstrate how we can write a PCR file and what is a data file, what are the output files it generates, and what information we can gather from that. And on the second day of the tutorial, we can look into how to make add another phase and do multi-phase refinement. Okay, and what are the information which are there. And maybe at the end of today's lecture or by evening, I will send some of the data files, which I think Dr. Rashid can share with you. And you can work on that. And tomorrow we will discuss that part also, if you like. Okay. So with this, I would like to start. So what we'll cover today is we'll see what is powder diffraction, how to reach to the data analysis, and what are the steps required, and how we approach our data analysis for structure refinement. And we'll go to the Rietveld refinement method. We'll see what are the information required, how to collect data, and how to carry out the refinement. And we'll be using some examples here and there to cover these points. So when you compare with X-ray diffraction and single crystal diffraction, the first thing is why diffraction is required. Okay, what information we are looking for in the first place. So the diffraction was in all earlier times before the advent of the high-end computing was done through single crystal diffraction. So you measure, after the X-rays were discovered, it was found that X-rays can be used for diffraction. You can actually deflect X-rays from the sample, which has a crystallinity. And you can actually collect those diffracted data, and you can analyze them and get information about the crystal. So the requirement for single crystal is that it has to be very, very pure, very pure. Any twinning or any tweaking in the single crystal will make it useless to determine the crystallographic structure. Okay, so the idea was that you measure all possible reflections of the single crystal. Okay, and you will get what is known as the lowest pattern or lowest cone. And each point which you see here is actually represents an atom from the crystal. And you analyze this using the lowest method, the diffraction method, and you can actually determine the mirror indices and then calculate the units and positions of that. Single crystal analysis is most frequently used technique for determining the crystal structures. That means if you don't know anything about the structure, you have to rely on single crystal diffraction to get the information about the crystal structure. But in many cases, getting single crystals is always a problem. So the availability of single crystals is always a question. You have to have high quality. In case of X-rays, it has to be good enough that it doesn't absorb, but it should be big enough to scatter properly. In case of neutrons, it is more worse because you need a bigger crystal because of the slow interaction with neutrons, and it has to have very good scattering also. So single crystal is very, very demanding. So the next alternative is the powder diffraction. And the limitation of single crystal is that it doesn't, the analysis does not provide information about the bulk of the material. You pick a small part of the crystal and you do the refinement, or you determine the structure from that. So that may not give you the entire distribution. It may have multi-phase sample, it may have some other issues, microstructural problems, which we will not be able to understand from the single crystal. So powder diffraction has a certain advantage over that. Okay. The powder diffraction method started from sometimes in 1960 by Debye and Schroeder because of the Debye-Schroeder geometry we have today. And but it is still limited to qualitative and semi-quantitative phase analysis and for macroscopic stress measurements. So the single crystal generally, or crystal structure generally consists of the information of a material like atomic positions and what type of atomic species are present at what distances and in what time. It is basically time and space average of the periodic conformation of atoms. Okay, it consists information about microstructure, which are caused by imperfections, dislocations, and all kinds of disorder. Studies of microscopic stresses in compounds are both residual or from while sample preparation can be studied from powder diffraction. And for today's time, powder diffraction remains a crucial tool in characterization of materials with increased importance, so that because of the increase in the application of instrumentation methods, analysis, modeling has become powerful and qualitative. So the principal problem, of course, with powder diffraction is that there's a systematic peak overlap of as you see in the diffraction pattern. Okay, and another thing is that what information you get from 3 dimensions from a single crystal is compressed into 1 dimensional in case of a powder diffractometer. But thanks to a person known as Hugo Rietveld, he was the one who actually determined this problem of peak overlap. Okay, so let's say, for example, you have one peak which you can see from a naked eye from a diffraction pattern, but it actually is a combination of 2 peaks. It's a resultant peak which gives you the single peak. So the method of use, what Rietveld said was that the method of using the total integrated intensities of the separate groups of overlapping peaks in the least square refinement method leads to loss of all the information contained in often detailed profile of these composite peaks. Therefore, he came up with a procedure in which these individual peaks could be identified from their atomic scattering, and you can actually get the intensity and position of these peaks to carry out a full profile refinement instead of relying on a single overlapping peaks, and get precise information about the composition of the sample as well as the position and unit cell parameters of that. So with the help of these initial papers, Rietveld method was established for powder diffraction, and instead of using a high intensity peak or choice of peaks, the full profile was used, and hence the program Fullprof was coined for full profile. And the full profile refinement method for actually was started with for nuclear or magnetic structures, basically using neutron diffraction. And the application of this method for X-ray powder diffraction by Young et al. Actually increased the reach of Rietveld method as we know it today. Okay, so initially there was very few papers which were using Rietveld method, but once it was started applying for X-ray powder diffraction data, the usage jumped like anything. Like what we are seeing that nowadays it is almost impossible to publish a paper if you are working on these areas without a proper Rietveld refinement of your diffraction data. Now, if you look at the powder diffraction data, actually this is the information. This is what you get from your diffractometer. Okay, so it has what? It has something called background. It has something called reflections. Now, if you look at them carefully, they consist a lot of information within them. The background can be because of the sample, which means it can be from the Compton scattering or diffuse scattering. If you do local structure or amorphous fraction, you can understand what type of scattering it is. Scattering, the background can also from the sample, can also be from the sample holder. So it is important to distinguish between these two using the proper software tool. And the reflections or the Bragg position, peak positions can tell you about the position of the intensity as well as the peak shape. The position will tell you about the lattice parameters or space group of this sample. And if you carry out micros, you can also carry out strain qualitative phase analysis using the lattice parameters and space group information. The intensity of the peak can be from the crystalline or magnetic structure. And it has information from atomic positions, magnetic moment, temperature factor, occupancy, texturing, and so on. And by using qualitative phase analysis, you can understand or qualitatively understand what is this all about. The profile can be from the instrument function. It depends on which instrument you are using, or it can also be from the sample. So if you are working on a nanostructured samples, you will see that the instrumental function becomes very important. The peak shape, the width of the intensities, width of the Bragg peak increases. And if you can model that, you can actually understand about the microstrain or the domain size. So we'll take some examples which will deal with all this in our next class when we do the tutorial. Okay, so the roadmap is actually starts from your sample, which is a powder, probably a black powder, and our aim is to reach to the structure. So what are the road or what is the route we have to take? The first is once you prepare the sample, you prepare the powder sample, well-grounded powder sample. you look for the radiation source. You can choose X-rays or neutrons. Okay, and based on that, you collect your diffraction data. You carry out what is called as indexing, determine space group. Then you can do whole pattern or profile fitting called the Liebel method. There is one more called Paulus method, but we will stick to Liebel method in this workshop. And then apply the chemical information and structure to carry out the structure analysis to reach to the final structure. So the first thing is the data collection. You can do a lab source XRD, which is usually available in most of the labs. That is the most prominent one. We all be using on that, and we will be talking about this lab source XRD in these demonstrations in this lecture. But there's something called synchrotron XRD, which is also very reliable because of the wavelength and the accuracy and the resolution of the synchrotron X-rays. Another part is the neutrons, which is it can continuous wavelength neutrons from the reactor source, or it can be time of flight from a spallation source. So neutrons are very important for studying the magnetic structures. It can also give you the information of the crystallographic structure also, so which is a complementary of what you get from the X-rays. Okay, if you look at the X-rays or neutrons, if you want to compare that, so X-rays has what is called as the atomic number or atomic weight dependence. What it means is that the heavier the atom, the more will be the X-ray scattering for that atom compared to the lighter elements. In case of neutrons, that is not the case. Neutrons doesn't scatter as function of the atomic number, but they scatter as function of the nuclear energy levels. So they have some advantages and then disadvantages of X-rays. Another point is that in case of X-rays or neutrons, the form factor or the scattering amplitude of X-rays falls off as function of the angle. Okay, what it means is that as you go higher in 2 theta, your intensity of the black peaks comes down. So this I think you would have observed in your XRD patterns. And the reason for that is that the scattering amplitude for X-rays fall off as a function of this 2 theta, which is not true in the case of neutrons. Neutrons have a almost constant scattering factor all through the angular region. Okay, now there are different type of geometries involved in case of powder diffraction. Okay, this is comparison for X-rays and neutrons. In case of X-rays, we have not what is called as the Bragg-Brent geometry, which works in the reflectance mode. What I mean is that you have a X-ray source, you have sample. The X-ray, since it cannot penetrate deep into the sample without being absorbed, so it has morely a surface kind of behavior, means it gets scattered from the surface. In case of neutrons, this is mostly they use what is called as the Debye-Scherrer geometry, which means it's a transmittance geometry, which means neutrons passes through the samples, it scatters all around, and we put detectors on this cone and measure the diffracted pattern. So this is one typical example for one compound which we'll encounter later also. This is the same sample at almost identical wavelengths, 1.54 angstroms for X-rays, and neutron diffraction, it is at 1.48 angstroms. The same composition shows different patterns, and the reason for that is as I said, is this scattering of X-rays as a function of atomic numbers, which is different for X-rays and neutrons. Okay, so the first step on our road to structure determination is called indexing. So if you have some idea about crystallography, okay, so you have known you should be aware of what is term called Miller indices, right? So a peak in the diffraction pattern is observed because of the diffraction from that particular plane. Therefore, the indexing is a process by which reflection indexes or HKL values are assigned to the peak in the diffraction data. For a cubic structure, actually you can determine cell parameters from one peak, from one index, and it should be identical for any of the HKL values or any of the peak which you choose. In case of tetragonal or hexagonal, you need at least 2 peaks. In case of orthorhombic or any low dimensional systems, you need 3 or more than 3 peaks to determine the cell parameters. So compared to indexing in terms of single crystal, where you have three angle parameters like phi, xi, and omega, the process of indexing powder diffraction is much harder since three-dimensional information is reduced to one-dimensional set of D spacings. So what we need to do is, if you look at the diffraction databases such as ICDDF, BCPDF, or JCPDF, okay, what they determine is the HKL values of the strongest Bragg peaks and the angle or D values. So what we measure is generally in 2 thetas. So using Bragg's equation, you can actually convert it into these spacings. So you have HKL values from the measurement. You compare with the literature values, assigned these milliindices to these Bragg peaks, and you can actually mark the D values from your observed data, HKL values from the database. Using this HKL and D values, you can actually determine the cell parameters. So that is the purpose of doing indexing. Okay, and what indexing and getting the cell parameters will also tell you what type of crystal lattice it is, crystal system it is, whether it is cubic, orthorhombic, or tetrahedral, and so on. And there is some constraints on the crystallography. That means you can, there are some relationship between the unit cell parameters and reciprocal space for different crystal systems. Okay, so this is something basic solid state physics which we would have learned in our 12th standard or in BSc course. Okay, so in the reciprocal space, we have the relationship between the HKL values and D spacings. Similarly, in the real space also. So we calculate our lattice parameters using this relationship. So if you have a HKL value and known value for D, for that HKL value, you can actually calculate the cell parameters for a cubic system, and likewise for the other crystal systems. Okay, there are several computer programs which are available for doing this indexing. Something is called ITO. There is something called Treror, which is basically a trial and error method. There is something called DickWall, which also does the same method. So you can actually do this indexing using these softwares also. You can do it manually also if you have the database and you know how to do that. And there are other programs who are also developed for manual indexing for diffraction patterns such as LASY and all that. But these are all old generation programs. Nowadays, very few are available, like ITO or Treror, which can do this job. And the one program which we had discussed with you is the PowderX software. So this is a Visual Basic based software which actually is useful for carrying out indexing of this program. So this is one example which I have done. You can actually import your data file, and you can actually mark the peaks. So it will give you peaks in D, in 2 theta D, and it will calculate the area and all that. So what you require is D spacings. That means it marks the peak, and based on this, once you have chosen the peaks, you can actually try the Treror method. Okay, this is a VB version of that method. Okay, so you can use the current peaks and sorry for that. You can use the current peaks, okay, and you can actually start the VB Treror program. Nowadays, I don't think you have for compiler, so it's better to use VB version. And you can actually, it can actually, depending on the quality of your data, it can actually give you some suggestions like what symmetry class it has, what are the possible cell parameters, and what could be the using these initial values, you can actually carry out the indexing of the peaks, and it will calculate this, define the cell parameters also. So it requires initial cell parameters. It requires initial HKL D positions of the Bragg peaks to generate the list of HKL and D values. So once you do, if you calculate and do the peak match, this is the information you get, which means that you can index all the Bragg peaks, and at the same time you can then refine the cell parameters. Once you refine, once you have identified all the Bragg peaks, you can actually do the refinement. So this is the information you get. This is your starting values of ABC values, and this is the defined cell parameters. So now what you have is HKLD values, and you can have a refined cell parameters. So once you have the cell parameters, you know what type of crystal system it is. You have indexed the pattern. The next step is to identify the space group. Okay, now you know that from the refinement, it is a hexagonal structure or a trigonal structure. So it can be any of these space groups. So there's some program called check group in the Fullprof suite. You can use integrated intensities. You can use WinPlotter and the raw data file. Get the integrated intensities for that from that. And using this integrated intensities for the powder data, you can ask the program to suggest you some space groups. And depending on the space groups, what type of crystal system you have, you know that. And depending on the cell parameters which you have, you should identify the systematic absences of that space group which are allowed or which you have observed. So it's a combination of that. It's a trial and error method. So you will come to a set of space groups which satisfies those conditions of the HKS and cell parameters which are obtained. Okay. So this is done automatically using Select program for a single crystal, but for powder diffraction, it is a little bit evolved method. So the best way of doing Rietveld refinement is that you should have a starting model and use that model to use that space group, that cell parameters to define or identify the cell parameters for your sample. Okay. So the next step, once you identify the space group, is to carry out the label fitting. Okay, so label method is basically extraction of intensities from the powder diffraction pattern, and it uses two-step cyclic process. So these are the parameters which can be fitted by standard least square methods. So cell parameters, alpha, beta, gamma, and ABC values. Instrumental zero error corrections can be done. Half-width parameters can be identified, and other speed shift parameters can also be fixed. So if you, as we will see, Fullprof is basically two parts. One is the instrumental part, one is the sample part. So instrumental parameters can be fitted using the label fit. So once you fix these parameters, then you are worried only about the instrument, the sample part. Okay. So if you look at the any PCR file, okay, this is how it looks like. So it has what is called different numbers, different. This is the PCR file I have opened in a text file. Okay, it can be any text editor you can use. It can be gedit, Notepad++, Notepad, WordPad, or any text editor. Okay, if you look at the PCR file, it tells you about what are the job types we are trying to use. This example, it talks about the neutron case. Okay, so if you want to find out more about the PCR file, what are the contents, I strongly suggest that you should go to this. Once you have installed the WinPlotter, you will find this Fullprof manual. You can use the HTML format if you have affixed to that, or you can go to this directory and open this file fpframe.htm and go to this description of the PCR file, and then you will find line by line description of what each of these numbers mean, okay, and what are the parameters it represents. Okay, so it is very important that you understand the PCR file properly before you start doing the refinement. Otherwise, it's just numbers which will be very confusing. Okay, so this is one example of the entire PCR file which has been written for carrying out the label fit. So in case of label fit, what is the important thing you have to do? Given the job type has to be true. Okay, we are now have the information about the space group. We have given the unit cell parameters to start the refinement of the label fit. What other information it has is that we have identified some background points. Okay, we have put the background points manually and put it here, and we want the program to do the linear interpolation between these background points. Okay. I will show you tomorrow or maybe later in this lecture on how to identify or how to pick out these background points. Okay. So this is an example for X-ray for neutron case, but the same procedure can be done for the neutrons also. But you have to do similar what is called appropriate changes for X-rays and neutrons. So I will come to that. Okay. So once you start, you have the PCR file. You can start call the PCR file, and if you have the DAT file of the same name, it will run the program and it will do the label fit. So at the end of the fit, what we have is that the space group which you have chosen is correct. It fits the entire spectrum. Our cell parameters are correct because all our peak positions are matching. So there is no peak which is not indexed or not fitted. So which shows that right now we have a space group which is correct. We have cell parameters which is correct. We have certain instrumental parameters which we have fitted using the Liebel fit. Okay, so next step would be provide the input structural information. Okay, so what is our structural model which we want to refine and fit to our observed data. Okay, so the chemical composition for my sample I know which I have prepared is calcium 3 cobalt MnO6, and because it's an it has ionic bond which has cation and anions, I have to do the balancing. So I know calcium 2 plus, cobalt 2 plus, and magnesium 4 plus, and oxygen is always 2 plus. So if I do that, it balances my equation. So this has to be my composition. So this 3116 in calcium cobalt MnO6. Okay. So now coming back to the space group, there's something called Bilbao crystallographic server. You can go to this website at https://ehu.es, and you can look for the Wyckoff positions. You have to give the space group number, or you can actually identify R3 space group, which we have confirmed from our Liebel fit. And if you look into that Wyckoff positions, it gives you the set of positions or coordinates at which the atoms can be placed. Okay. So similarly, you can also find out the space group information from your Win plotter. Go to Tools, go to PCR Group Info, just type in the space group, or you can type in the number also. Okay. If you know the number, space group number, you can type in that, or you can just type in this in certain format. So it will give you information on the space group. So it will give you a total, what are the space group numbers, what are the Hall symbols, and things like that. What is important is the general multiplicity for the space group. And we are interested in finding out the multi-site, what are the Wyckoff positions or special positions for the space group. Okay. So in case of R3/C, it is 36. And in case it has 36, what it means is that it has 36 positions at which atoms are. It is possible to put an atom. But there's something called Wyckoff, special Wyckoff positions also from the geometrical point of view. And these are identified as this. These are also actually part of these positions. Okay. So if you go, it has something called site symmetry, site multiplicity also. So you have multiplicity, you have site symmetry, and we have positions at which atoms can be placed. Now, how the atoms are chosen is that you take one general position, you have to take position in such a way that it actually satisfies your geometrical conditions also. So when you test these positions in refinement, your position, atomic positions and scattering, systematic abscences have to be correct. Okay. So you have to place certain elements at these 4 sites. So how I done this, that calcium I have put at 18. Yeah.
Sorry for disturbance.
Yeah.
Actually, some noise is coming.
Now is it okay? My mic was far away.
Yes. That's fine. Yes.
Yeah. My mic was little off. Okay. So thank you. So now, the calcium. So in my composition, I have calcium, cobalt, magnesium, and oxygen. So my calcium is at, I can put it at 18 east side. So the position, general position is X0Z. X I have to either determine from the crystal from the database, or I can refine the starting value and get to this values. Similarly, cobalt I can place at 6A position, which is 0014. This is a special position, so there is no possibility for me to refine this one. Okay. Similarly, manganese is at 6B position. Again, this is 000, which is actually the origin of the unit cell. Okay. Now then oxygen is 36, which is basically a general site. So I have X, Y, and Z positions. Again, the value of X, Y, Z has to come from the crystallographic information about this sample. Either I have to refine it or I have to fix that. Use the literature value to start with. Okay. So if I don't know what the exact value for this Ca3COMnO6, what one can do is that you take the nearest best equivalent of this one, maybe isostructural or isotypic, Okay, instead of calcium, it can be strontium. Instead of cobalt, manganese, it can be any two transition metals. But it has to follow this K4 Ca3 3116 type of nomenclature. Okay, so if it satisfies that condition, we can take that as a starting values. But since you have defined the cell parameters, you can use the cell parameters from indexing and Lie fit. You can take that as a starting value. You can take this as the atomic positions. And the reason of doing this exercise is that if you see the site multiplicity, it is 18,6,636, which is basically 3116 ratio. So the occupancy which I have taken for this site, so my 100% site occupancy is site multiplicity divided by the general multiplicity. So 18 by 36 is 3. Okay, so 18 by 36 is actually 0.5. But what it means is that this ratio of 18,6,636 is basically 3116. So my composition, if I take it in this format, will always be correct. Now, actually, many people work on oxides or intermetallics where do this cation substitution, or this like alloying. So where you are substituting one for the another one. So in those cases, getting occupancies correct is very important. Otherwise, it will affect your fit. It will affect your composition. It will affect your refinement also, right? So the next part now, once you have all the information required, you can do is that implement it in your PCR file and carry out the Rietveld refinement. Okay, we'll come to that part in tomorrow's lectures when we see how we do actually the refinement. So this part, whatever we have done, so it's the same example we'll do tomorrow also, and we will see how we can start the refinement and reach to the solution, what information we can extract from the powder diffraction data. Okay. Okay, now what are the advantages of Rietveld refinement method is that we are using the measured intensities as it is, which means we are not doing anything with the obtained data. So there's no manipulation of data, no tinkering with the data. We are taking it as it comes. Okay, we are not changing anything. So, and we are using the entire spectrum, the entire profile from say 10 degrees to 80 degrees or 20 degrees to 70 degrees. Whatever profile you are measuring, you are using that. The advantage is that you can do qualitative phase analysis, you can do quantitative phase analysis, you can refine lattice parameters, atomic positions and occupancies. As I said, if you're working with a series of samples with small substitutions, so it will give you a graded information about how the lattice parameters are changing as a function of the substitution. Okay, if you are working doing temperature dependent X-rays or pressure dependent or magnetic field dependent X-rays, you should be able to follow this changes in the parameters as a function of that external parameters. So it gives you a qualitative analysis. It gives you a very good picture of how the system behaves in different conditions. The Debye temperature is also an important quantity if you are working at high temperatures. So you can see that which of the atoms have a tendency to move out from its position, and which is the one which is actually, in case of ferroelectrics, it becomes very important. Okay, so which are the parameters which are causing the distortion or reducing the symmetry or breaking the inversion symmetry. Okay, if you are working with nanoparticles as a function of say substitution or as a function of milling, okay, you can also track the grain size. Okay, and you can actually match grain size with any other physical quantity which you are studying for those samples. You can also look at the macro strains. Okay, so there is a set of parameters which you can obtain as a function of because of the Rietveld analysis, and it can be as a function of temperature, pressure, magnetic field, and so on. And the Rietveld refinement method is the best way of determining magnetic structures. And if you are working with magnetic materials or any ferroelectric or functional materials, you can correlate your structure and that physical properties as a function of the substitution or the pressure or the temperature, whichever quantity you are varying. The disadvantage of Rietveld refinement method is that it is the refinement method. What it means is that it requires a starting model, and it has to have a very close resemblance to your starting model. Okay, so if you start with a sample with a starting model which is not close to your model, then you will never reach to the actual result. Okay, so some prior knowledge of crystal structure is required. You have to understand what is space group and what are the symmetric conditions. And Rietveld programs are basically statistical programs. They are not easy to use. Okay, so that is the reason why we are here, and you need some experience to analyze the powder diffraction patterns. So yeah, it's not that in one day you will learn it, but probably if you keep practicing, if you know what is to be done and what not to be done, I think you'll reach to that very easily. Okay. Okay, so now coming to the method, what is actually Rietveld refinement method? Okay, so you are using a crystallographic model and we are computing a corresponding powder diffraction pattern. So based on certain equations, we are generating a diffraction pattern and we are actually matching it with the observed data. So we are trying to simulate the pattern. Okay, we are refining this model, the experimental model, which is there in the PCR file. Okay, so we are actually manipulating the PCR file, the information in the PCR file. We are changing the lattice parameters, we are refining the lattice parameters, we are refining the background, we are refining the atomic positions, and we are trying to match it to our actual data. And the reason for doing that is to minimize the difference between the observed pattern and the calculated pattern. So what is called the least square sum method, because we are trying to reduce the difference between the sum squares of these two quantities, that is observed intensity as well as the calculated intensity. Okay, so the observed intensity is given by this equation, and in a minute we'll come to this equation and we'll see what are these parts, what are the important constituents of this equation, which are the ones we are going to refine. Okay, what basically we are doing is that least square method or the Rietveld refinement method is the iterative method. So we are actually refining certain set of quantities, and we have given certain boundary values, so that if the difference between the two successive cycles is beyond a minimum necessary condition, then it will go to the next cycle. Otherwise, it will converge. Since it is a statistical program, the idea is to minimize the difference so that the refinement cycle can converge at a certain point. The values at which it will converge is the minimum of that particular quantity. Okay, so we are refining say 5 quantities. It has reached the minimum of its value, it will converge. Otherwise, it will go to the repetitive cycles till the number of cycles we have specified. Okay, so the shift in the parameters which are obtained by solving normal equations are added to the starting parameters, which gives a next starting values, and the cycle goes on till it converges. Okay, so it is all part of our exercise which we are doing in the PCR file. Okay, so the optimization method is that the least square procedure provides, when it converges, the value of the parameter constituting the local minima closest to the starting point or the ideal value. A good set of starting values for all parameters is needed. If the initial model is bad, for some reasons, the least square refinement will not converge and you will not get to the ideal values which you are looking for. Okay, as far as powder diffraction is concerned, X-rays and neutrons are almost identical in terms of refinement also, but the difference comes in this equation. This is the equation for the structure factor, which is the most important quantity in the generation of the calculated diffraction pattern. So in case of X-rays, we have what is called as the X-ray scattering structure factor, which depends upon the X-ray form factors. Okay, and this is the equation which has a position, XYZ position of the atom. HKL values are the planes from which the particular atom reflects, or the Miller indices, which because of the reflection coming from those particular set of positions of atoms. Bj is the thermal parameter. Sin square theta or sin theta by lambda is actually the scattering function which we are using. In case of neutrons, this is called a neutron scattering length, Bj, and most of the equation remains the same. So the procedure for X-rays and neutrons are not much different except for some minor changes. But what we are actually doing is that we are calculating in powder intensity of powder diffraction P, and we are trying to match it with the observed from the simulated ones, which are calculating using these equations. So the intensity is always proportional to this structure factor. Okay. So if we look at this XRD pattern, okay, this is for the same composition, calcium 3 cobalt manganese oxide, and we have measured at room temperature using X-rays at 1.54 angstroms, which is copper K alpha wavelength, and we have done it on our diffractometer at Dhruva at we're using 1.48 angstrom neutrons. If you see the difference in these patterns, okay, they are for the same angular range, but you can see the certain peaks, the intensity is very high. In case of X-rays, the intensity is very small in case of neutrons. In case of X-rays, the intensity is very small. In case of neutrons, it is very high. And the main reason, as we have seen above, is because of these scattering coefficients in case of X-rays and neutrons. If you observe this carefully, the calcium for cobalt, manganese, which are heavy elements compared to oxygen, the scattering is high. And for case of oxygen, it is low compared to this. But in case of neutrons, you have almost identical scattering factor. In fact, oxygen is the strongest one. So if you are working with oxide materials, you have to choose your radiation carefully so that you can get the best, you can use the best radiation source for getting the best values. Okay. So this is the main reason why you see that certain peaks have better intensities in case of X-rays and neutrons have better intensities for certain peaks. And using the same structural model, I can refine both X-rays as well as neutron with a very good refinement parameters in both the cases. Now, coming back to the equation of which is used for calculating the intensity of from the information which we provide in the PCR file. Okay, each of these quantities can be actually been written as a parameter in the PCR file, and these are the values which are going to refine. Okay, so if you just look at that, one is the scale factor. The scale factor actually is given by this equation. What it means is that it tells the program from which part of the diffraction pattern you have to start assuming this, you have to scale the intensity. So then only the intensities will match. If your scale is correct, and scale is something which will refine all the time, so that any changes should not affect the intensities. So the intensities will be proper if our starting point is correct. So that is our scale values. So it will put observed and the calculate pattern on the same scale based on this information. Second is the polarization factor, which is called an instrumental geometrical function. Okay, it can be because of the transmission geometry or the reflectance geometry. It can be Bragg-Mehta or Debye-Scherrer method. So depending on the instrumental function, there will be a polarization factor which is inbuilt in the PCR file. There is something called the structure factor, so which we have already seen. It is a combination of our atomic positions, cell parameters, the thermal parameters, and so many other factors which we have already provided that information in the PCR file. Okay, so based on the information which we provide, based on the number of atoms, number of what type species of atoms there are, what are these crystallographic conditions like space group and positions, it will scatter and it will generate the Bragg peaks according to that structure factor. Other is the shape function. So for different diffractometers, like whether X-ray or neutrons, you have a peak shape function, right? It can be Gaussian, it can be pseudo-word, it can be Cauchy, it can be Pearson's, and so on, depending upon the electronics and the arrangement of that instrument. Okay, so this we have to mention what type of peak shape we are going to use for refining our diffraction patterns. Second is the number of peaks. That depends upon the symmetry and the space group. So in case of cubic samples, as we would have observed, the number of peaks are less because they are very strong reflections from certain peaks only, so certain Miller indices only. In case of monoclinic system or low symmetry systems, you have more number of Bragg peaks which contribute independently to the diffraction pattern. Okay, so you may end up with having peaks getting overlapped in case of low symmetry systems. And some people actually study texturing or preferred orientation, as it's called. Like in thin films, you have preferred orientations. But for a powder diffraction sample or for a powder diffractometer, it is not a desirable quantity. If you work, the reason why it is called powder diffraction is that because you want to have what is called random average instead of having reflections coming from a particular reflection, particular plane, we want it come from the random orientation. So that is the reason we make it a powder. It has to be as good as fine as possible to avoid preferred orientation. So it is a small if it is in small measure, it can be refined and you can actually quantify how much preferred orientation you have. But there is a limit to that. You cannot have very strong peak and rest of the peaks are very minor. It will give you a false information. Okay, and there is something called absorption factor. This is mainly useful or it comes into picture when you are working with the transmission geometry, because the radiation passes through the sample and the chances of it getting absorbed are very high. It works probably with neutrons, but if you have very thick sample, maybe the sample is not properly aligned. In case of X-rays, then it is possible that some portion of your beam is getting absorbed within the sample, and that has to be corrected at some point. And of course, the background function. Okay, so as for determining the scale, you have to determine the background also. So the background function, in case of Rietveld, you can actually use a polynomial. You can actually pick up the points and ask the program to do linear interpolation between them. So it's up to you. There are different functions which are available in the program, and you can also use. I generally pick the points and provide it as a function, and ask the program to do linear interpolation between that. Okay, so this is one. Depending on what kind of data you have, you can use this background function. Okay. Now, how do you evaluate the Rietveld programs? There are different R values which are generated when you do the refinement. Okay, something is called RP, or the Rietveld profile parameter, which is basically the ratio of the difference of observed and calculated intensities due to the observed intensity. Okay, then you have what is called a weighted pattern, weighted profile, RWP. RWP is basically it has some weightage which is provided. Basically, it works on the square of the differences between them. Okay, then you have what is called as the Bragg factor, or RB values, which works on the integrated intensities of observed and calculated peaks. Okay, and then you have something called R expected, which works on number of parameters being defined to the number of actual data points you have. Okay, so if your data quality is good, your R expected values will be satisfactory. If your data quality or number of points or number of parameters being defined is different, or if quality of signal is very poor, then you will end up with a very high R expected values. And the goodness of fit is basically the ratio of RWP and R expected. Okay, so RWP being low and R expected being high will give a false minima. It cannot be less than 1. Okay, because the RWP is the lowest value R expected can go. Okay, it cannot be less than that. So that is something we have to keep in mind when we work with our refinements. And how do you evaluate the fitting quality, or R factors? What is the acceptable values? RWP is the most valuable parameters in evaluating the refinement. You should always keep an eye on RWP value rather than on chi-square. Okay, chi-square can up to 5, 6 is acceptable if your RWP is less than 10. Okay, for RWP values for medium or complex samples, this should be less than 10. For very high, very complex or like low symmetry systems where you have overlapping peaks, it can contribute to high values of RWP. For high symmetry systems like cubic and all, it should be less than 8. That is the ideal values, ideal conditions. Okay, so there are certain points like our samples can be with high background can have very high RWP values. And R expected, as I mentioned, is the minimum RWP value can reach. And so S or chi-square less than 1 has no meaning as such. Okay, it can be 1 or less. In ideal cases, it will be less than 2 or around 2 to 5, between 2 and 5. Okay, that's okay. Okay, so the weighted sum of squares, basically this is again the sum of the squares and with some weighted scheme of observed and calculated pattern, which is our chi-square. This is used to minimize the subroutines. We should always keep an eye on how the chi-square is varying. it should progress in particular direction. It should come down, okay, from your initial fit. Okay, so the goodness of fit is the ratio between RW between R expected and cannot be less than 1. And a good refinement value of goodness of fit values lower than 2 or around 2. For noisy patterns, it is quite easy to reach a value near 1, but it is not very good index. And goodness of fit is sensitive to the inaccuracies in the model. So if there is some problem with your starting model, you will never have a good goodness of fit value. Okay. So now, what is the procedure which we can adopt? Okay. Just a second. Now, to do a meaningful refinement of your sample, you should choose your experiment carefully. You have to choose the correct instrument depending on what actually you are looking for. Okay. So if you want to look for a magnetic structure, X-rays are not going to help. So like that. And if you're looking for precise cell parameters, X-rays will help. Neutron diffraction has a poor resolution than X-rays. So X-rays are equally important, right? So you have to choose your experiment correctly depending on what you're looking for. You have to select the experimental conditions, which means at what temperatures, what magnetic fields, what pressures you want to do the experimental conditions, okay, or compositions, which compositions you are trying to study. Okay, you have to prepare your sample, which means you have to, when you are doing powder diffraction, it has to be really powder, very fine grounded powder. Okay, you have to have proper quantity of the sample so that you collect good quality data. Okay, so when you do the experiment, you have to make sure that you get good signal to noise ratio, okay, which means less noise and more number of intensity, good intensity and less noise. Okay, so once you get the do the experiment, you have to verify the quality of the data and you have to perform the qualitative analysis. Okay, so for Rietveld refinement, you have to choose the correct starting model, choose the proper model which is isotypic or isostructural to your sample. You have to adjust parameters like cell background parameters. You define the background, you always define the scale, define the peak position, peak shape, define the structure. Okay. Choice is that you start with the scale parameters, cell parameters, background, positions, shape values, and the entire structure. Then you can assess your results, whether how it looks like. For successful Rietveld analysis depends strongly on the quality of the data, quality of your experiment. Depends upon the instrument characteristics and assessment, choice of the instrument options. The strategies you should check is the range of samples. Okay, what is the blue theta range you are looking for, depending on where you are expecting the strong peaks in the diffraction pattern. What should be the step size? Too broad peaks, too broader, this bigger the step size, broader will be your peaks. Okay, and there is a limit on this. This limit comes from the instrument. Okay. Most of the X-rays, they work on a regime of 0.02 degrees step size. Most of the neutron instruments, like the one which we have, works on a regime of 0.0304 degrees blue theta as the step size. Okay, that is the resolution you are getting. For how much time you are measuring your sample. Okay. And it also depends upon the size and preparation and conditions of the samples. There are several programs which are available, like GSAS, Fullprof, the mod, Retan, and all this. Most of them are free. There are some commercially available also, like BGM and Topaz, and I think there are some more softwares which are available. We are working with the Fullprof for the main. First reason is that it is freely available, and the most important reason is that it is currently under development for last so many years, and you are getting a latest update on this, and it works with almost all platforms, and it is quite versatile. Okay, we can do both X-rays and neutrons structure as well as magnetic structure refinement using Fullprof. So that is quite important. Another thing is that it comes with a lot of programs which is inbuilt within the Fullprof, like Fullprof Studio, which is useful for visualizing crystal and magnetic structures. Then you have WinPlotter and WinPlotter 2006, which is 2006 is useful for working with the magnetic structure refinement also. Then you have a non-GUI based Rietveld refinement program, which works on, I think, DOS mode. Then you have an editor for PCR files, which is a GUI based editor, EDPCR. Most of the students, I think, nowadays use EDPCR, but there's a small bug. I will tell you what it is. And for that reason, I use the text editors for working with PCR files. Then case search is there, which is useful for working with magnetic structures for identifying the propagation vectors. Then there are something Trello and Dickwall, which is useful for indexing, as I told you earlier. Instead of PowderX, you can use these programs also. There is check group for checking the space groups. There's for single crystal data reduction, there is some softwares, and there are other programs also like bond valence sum, G Fourier, Basireps for magnetic structure symmetry analysis, and so on. Okay, so these are suite of programs which are available. You can spend some time on that. We use your data. It is quite quite interesting to work with that. Okay, just getting started, you need a PCR file. You need an input file basically, which should contain the information about the crystal sample. Actually, if you are working with a crystallographic structure, it should contain crystallographic structure and instrumental part. Okay, like wavelength, what is the 2 theta range, what is the step size, what are the half widths, and so on. So there are two parts basically. One is the crystallographic part, one is that is sample related, and one is the instrument related. Then you have you need another file. This is data file like .dat, and it can be in any format which the Fullprof can read. Okay, so different instruments give you different formats. So that's okay. As long as the program is able to understand, it should be okay. Okay, you have to mention PCR and the DAT file. And if you give the same file name like a.pcr and a.dat, then you don't have to specify the DAT file whenever you run the PCR file. In case you want to use a different file name, that is also fine. You just have to specify what data file you are going to use. Okay, and the Fullprof will ask for a PCR file, and then it will ask for a data file. And when it goes through the program, it goes through these iterative cycles. It generates, depending on what flags you are using, it generates a set of output files. So all the information of the refinement is stored in this output file. If you have flagged PCR2, I will show you how to do that and why to do that. It will generate a copy of the PCR file, but with the refined values. Okay, all the refined values will be in this .new file. If you are satisfied with the refinement cycle, you can use this in the next cycle and overwrite the PCR file. Otherwise, it will the program is built in such a way that it overwrites it by itself. This is called summary file .sum file. Okay, it will have all the information with standard deviation and all contained in this output file. There is something called FST file. This is Fullprof Studio file, which will have the structure information. You can actually draw the structure using this FST file, and you can use that structure or that picture in your publications also. And this is useful for magnetic structure refinement also. It can show you the magnetic structure as well as magnetic moment also. So for each phase in the PCR file, it generates one FST file. Okay, then you have something called distance file, .dis file, and .bvs files. So these things tells you about the atomic distances, okay, bond distances and bond angles, depending upon the information which you have to mention in the PCR file. Okay, so this is something which we have to mention. So if you are working with a metallic bond, you can calculate the distances. If you are working with ionic bond, you can calculate distances as well as bond valence sums. Okay, so to understand bond strengths. So okay, so these are the output files which it generally generates. So can starting with the PCR file. So how to get a PCR file? So first way is to use a CIF file, what is called as a crystallographic information file. Okay, so you can get the CIF file, and there's some tool called EDPCR where you have a subroutine for converting CIF to PCR file. Now the PCR file you can get from many of these databases. Some of them are free, some are paid ones. But there are certain journals which also provide zip file as a supplementary file. Okay. So some examples of PCR file are already there in your examples folder. If you install Fullprof suite, there will be one folder called examples. You can take any of the PCR file, use an editor, and modify that to suit to your sample. You have to replace the sample information according to your sample, and you have to replace the instrumental information like wavelength, the 2 theta range, the half widths according to the instrument which you have used. Okay, so this is a typical PCR file which I have used for a sample called PR SRMNO3. Okay, and how to input the data file format. So there is something called instrument here, and when INS is 0, it uses the data in 10 column format. So this is starting angle, step size, end angle, and the data in 10 columns. Okay, this is 1, 2, 3, 4, like that it goes to the entire set. Another file format which it treats is that instrument 10 is in the data usually in the two column format. So you have X axis which is the 2 theta, and Y axis which is basically intensity. So what most of the information which the experiments which we do on X-ray diffractometer will give you data in this 2 column format. So accordingly, you can modify your PCR files. Now, second is the background function. Okay, so when you have number of background points which you have to specify, if you say 0, then you have to specify the background in form of a polynomial. So you can use up to 6th degree polynomial you can specify and use. Or you can actually plot your XRD data, okay, and just blow it up. You can go to point selection and go for select background points, and you can choose your background points, save the background points, and you can actually collect this background points, and you can actually insert it in your PCR file at some position in the PCR file. And you have to specify number of background points which are done. So program will interpolate between these points and actually generate a background polynomial function. Okay. So this is the information about the structure part as well as the half-width parameters, cell parameters, and so on. So if you look at that, you have a number of, as per my sample, I have 5 atoms in the unit cell in the crystallographic structure. This is the space group, PNMA. And if I want to find out about the space group, as I showed, you go to the tools, space group info, and it will tell you what are the general multiplicity and what are the Wyckoff positions. Okay, so accordingly, you can see my positions are X14Z, manganese at 0, half. So praseodymium, strontium, they are at the same site. Okay, so I have to just reduce their occupancies accordingly, but they'll have the same atomic positions. Then I have oxygen, then I have oxygen 2. Okay, 2 oxygen sites. So now if I go back to the PCR file information, they have general multiplicity of 8 and site multiplicity of 4. So according to my positions, I have praseodymium and strontium at site 4C, manganese is at 4B, and oxygen at 4-1, oxygen 1 at 4C, another one is at general position 8. So accordingly, I had once I substitute that in the PCR file, this is the occupation or site occupation numbers which comes in the output file, which shows that praseodymium is 70% occupied, strontium is 30%, manganese is fully occupied, so are the oxygen sites. So this is what exactly we wanted, that praseodymium, strontium should be 70-30 and rest are fully occupied. So just to do a backhand calculation, you can actually find out that this is actually as per the stoichiometry. Second,
Sir,
yeah.
Sir, I have one question.
Yeah,
like we are not having all the time a crystal structures, like CIF information we don't have all the time for all the materials.
Yeah.
If we are working on composites or some kind of alloys or random alloys especially,
Yeah.
so in that case we have a parental peaks of some particular pattern from where we started the material. So in that case, if we take the CIF information as well as the crystal structure of that paternal parent, parental peak, like if suppose we are working on, let's say example, hexagonal substituent as well as monoclinic substituent. So we don't know the material where it will move, but in XRD pattern, the dominating phase we are getting that, like we are telling that 100% intensity peak matching with the hexagonal phase, but still it is shifted because alloys are not giving perfectly all the time complete peak shifted. They are slightly shifted also sometimes. So in that case, what and how we will generate the CIF file and how we will propagate with that functions.
The first thing is that you don't see if you have the isostructural, that's what I'm saying, something which is nearby your patterns. Okay, before you go into CIF file or go to Rietveld refinement, you have to index the pattern. Okay, you find either you do indexing manually or you do with label fit to identify what is the space group which satisfies these conditions. Okay, so if it has formed an alloy or it has formed an intermetallic alloy, then it will have certain positions, right? If it is a composite, then you have to do two-phase refinement. If it is same phase, then you can if it is a second phase, secondary phase is coming up, then you add that secondary, identify the phase and you input that secondary phase, and then you can do a qualitative two-phase refinement and find out what is the phase fraction.
Okay, sir. So it will come after, like after your primary structure, it will come again that I want to see that thing. If it will come in your lecture, Yes,
so
sir.
one of the examples I had taken where I will add a secondary phase and I will show you how it works. Okay, how to add a secondary phase. But for each phase, you have to identify what it is, what phase it is. So you can start with the main phase, and then you can identify the secondary phase, what is not from the main phase. You can identify the parts of the secondary phase, okay, and you then add the relevant information or relevant phase for that phase, and then you can refine that.
Okay, so first, like procedure start with the data file. Then we have to go for HL indexing for that file, space group and this, and then probable structure we have to apply. Like keep in mind that what is the binding pattern if you are assuming this with a particular temperature, and it will go from this to that movement. So we have to file out from that, or it will generate from there the CIF file or something like that.
No, CIF file you may not get for everything. Actually, you can generate a CIF file. I will show you how to do that from the refinement which you are doing. Okay. But to start with, you need a certain model. Okay. Some starting information you need. Okay. So it has to be something which is isostructural, or it can be, say, it is possible, like if you are working with an intermetallic, it may have become one of the phases would have become deficient. So that can be accounted for. Okay, you can look into that composition. You can look into the positions which have shifted. Okay. So so we'll do that. We'll try to add one secondary phase and see how it goes. Okay.
Thank you, sir.
Sure. Right. So if I continue now, next is So what you should do and you should not be doing is that when you don't have to refine parameters which are fixed, like as I said, fractional coordinates, like if it is 00 z 00 1/4 or 000 or 00 you don't refine those parameters. The lattice parameters are constrained by the crystallography lattice systems. Okay, so there are certain conditions, like in case of a cubic, all sides are same. In tetragonal, 2 sides are same and 1 is not. So like that, those conditions you have to keep in mind when you are defining. When you are working with trying to refine the half-width parameters, okay, so what you have to understand is that among the UV, W, and W, X, and Y parameters, U, X, and Y have influence from the sample. Otherwise, U, V, W, X, Y is basically an instrumental parameter. So you can refine U, X, and Y. You can adjust V and W and V depending upon the instrument which you have used at that time. Okay, but mainly, if you are working on a systematics of samples, then you have to look into U, X, and Y parameters only. Okay, so you have to keep in mind. And by the function, V is always negative, so you should keep that in mind when you refine. You should not refine blindly. You have to keep an eye on what is going on. Okay. In case of X-rays, most of the cases, this anisotropic or isotropic temperature factor becomes negative, which has no physical meaning as such. So the best strategy is to keep it 0, or if you have the values available from the literature, you keep those values fixed. Okay, don't assume that it can become negative and it is okay. Negative temperature factors have no physical meaning. And you should not use a narrow range of 2 theta values for refinement. You should use as broader range as possible. Okay, and you should not forget the number of structure parameters being defined, because it cannot be more than the number of lines. So these are certain errors which comes depending on how many parameters you are refining or how many parameters you have asked the program to refine. So okay, it can give you certain errors like hole in the matrix. Okay, you have to just check what are the parameters to be refined, and whether you have forgotten any parameters, defining any parameter. Okay, so like that, Fullprof is very sensitive to format. Okay, if you look at the PCR file in a text editor, you see that it is in a certain format, and any mistyping or like additional space or additional character at an undesirable space, this program will start crying. It will not go further. So you have to be very careful with the format also. And sometimes it gives negative FWHM error also. So you have to see how the parameters are. Okay, so it cannot be less than 0. It is meaningless. So you have to check the values and ensure that it is going in the proper direction. And there are certain other errors which are usually find that, like no scattering factor. So you have to identify the atom type which is given, which is not recognizable by the program. Like I said, it can accept Ca+2, but it cannot accept Ca2+. Like that, it can give you certain errors. It will not tell you what is wrong. It will tell you that it has not found that element. Okay, and certain other problems, issues like too many reflections. So usually this is because of the FWHM or UVW values. Okay, and invalid integer or invalid real, again it comes from some of the typic error in the PCR file. And the software always does not give the correct line at which you have to look. Okay, there are certain comments, so many things in the PCR file, so you have to be careful at what it means. And I think this comes with experience. The more you work on that, more easier it will be for you to understand. Okay. And tomorrow we will see in our first tutorial how to actually do the refinement. I will try to demonstrate it on my laptop, how to start with the PCR file. I generally use the text version or the notepad version for editing the PCR file. And if possible, I will try to show you with an eDPCR also and how it works. And we'll see how it works tomorrow. We'll try to see take as many examples as possible. And we'll make it less informal so that we can interact in between. If you have any issues, we can just talk through the program. Okay. And with that, I'll close my talk for the day. Thank you very much for your time and attention. Thank you very much.
Sir, thank you very much.
Thank you,
sir. Some students have asked some doubts.
Yeah.
You can see in the chat box.
Yeah, sure.
Please.
Okay, I'll close this and I'll come. Yeah.
Okay, sir. Okay, thank you.
Yeah. So, what are the questions? Okay. Yeah. If you have questions, just let me know. I'll try to answer.
Sir, I have one more question.
Yeah.
It's like when we have known structures, like let's say the cadmium sulfide or something like that, it's very sharp peaks are coming when we are going towards the bulk. But when we are moving towards the nanostructure, the structure is coming with a very broad background. Maybe it's very not easy. It's very noisy also, so it's not easy to get peaks from that extraction. It looked like almost a broad hump is coming, and then everything is merging. So whatever we are trying and along the scans and everything in an experimental way, it's always comes the thing. So it's a sample property, or it is like something else in that case.
Yeah. The very reason of you making the sample nano is that you're from the crystalline state. You're actually destroying this crystalline state and going to the nanostructure. So you won't get this crystallinity as such. Okay, so that's one part. Second thing is that when you work with the nanostructured samples with X-rays, you have to be very careful of the instrumental broadening also, right? So if it is done on the same instrument, if you do the bulk and the nano part samples on the same day, okay, so you will have the same instrumental parameters, and then you can see look into that. You fix the instrumental part, and then you will look into the sample broadening issues. Okay, so I have one example. I have planned one example. I will show you tomorrow how the same sample, when it is reduced in particle size, how it looks in the X-ray, and how we can refine that, and how we can get the particle size from that. So our interest is to look into the particle size. So we can look into the particle size from the X-ray refinement also. So I can show you that tomorrow.
Okay, sir. Thank you.
Sure.
Hello,
Yeah,
sir.
yes.
I have one question.
Yes, ma'am.
Sir, while doing the refinement,
Yeah.
when we choose the background points, okay, so
Yeah.
we have three ways. One, we can choose them by clicking the points, as you said.
Yeah.
Second way, we can do linear interpolation option. And third, you said that we can use a sixth polynomial.
Yeah.
Sir, what advice would you give? Which way we should go? Which is the better way to do that?
Yeah, so from my practice and experience, I find that if you have a flat background from the diffractometer, I think it is, then you can use a polynomial function like 3 polynomial, 6 polynomial, and you can use one of those coefficients and get the background fitted.
Okay,
Otherwise, the best thing is that if you have a curved background, it's best to pick out the points like I showed, and you paste it in the PCR file and let the program, or you can save it and you can call it from EDPCR also. That is also possible. Okay, so
Okay.
you can actually pick the points, okay, and you can do that. So that can be done automatically. You can ask for the program to look for the step size as well as the noisy data, and you can pick it yourself manually and you can paste it in the PCR file. That will also work. You have to specify a number of background points which are giving, and you can then refine the backgrounds also.
Okay, sir.
Yeah.
Sir, if we have to choose it manually, how many points should we choose? Like 70, 80?
See, it depends on the data range you have. You should avoid the bragg peak positions.
Okay.
And the more number of points means more number of points it will do the interpolation with. Okay, but you have to be very careful that if you have too many background points, your R values will artificially come down. Okay, but your chi-square may also go down. Okay, so you have to be careful. You have to avoid the bragg peak positions. And if it is a straight line, actually you can actually choose 3-4 points. But if it is a curved one, you have to take it carefully. Yeah, you can do that.
Oh, sir, I have one more question.
Yeah.
Sir, if say I want to do XRD on my pellet, and sometimes the sample holder plate is like the pellet is very small, 8 mm, 10 mm around diameter.
Yeah.
And I have to fix it using the clay.
Okay.
Sir, I think there is a chance that some peaks of clay might come in my XRD data.
No. Clay may not come because it is actually usually it is outside the beam, X-ray beam.
Okay, sir.
But the problem with the using the method which you are saying is that there is a depth, in your sample holder.
Yes,
okay, you'll have a certain groove kind of thing, right?
Yes, sir. Right, sir.
Your sample should not come out of that groove. Okay. And in case your alignment is not proper while measuring, see, in case most of the X-ray machines, which X-ray machine you are using?
Sir, it is Malvern Pananalytical.
So it is 2 theta geometry or theta geometry?
No, sir, it is 2 theta geometry.
Okay, so in 2 theta geometry, what happens is that your sample also moves, okay, as a function of theta. Okay, so it will actually misalign. So at higher angles, you will have certain intensities which is not from the sample. Okay, it is an artificial intensity. Some preferred orientation will come.
Yes.
Things like that. So alignment has to be very proper. Okay. So it is always better to use powder sample, fill up the sample space, and try to avoid using pellets. It will give additional, so as I showed you, it will give you preferred orientation in some cases. Okay, so you have to be careful when you refine that.
Okay, okay, sir. Thank you so much,
Okay.
sir. Sir,
Sure.
I am a Kiran sir student in NIT Jalandhar.
Oh, nice. Hi, hi.
Yes, sir. It was very nice attending this lecture, sir.
My pleasure.
Thank you so much, sir.
Thank you. Thank you. Yes.
Sir,
Yeah.
I have a question actually.
Yeah.
Sir, in your today's lecture, you mentioned about through this refinement we can identify the substitutions in the metal oxide. Say for example, we can in iron oxide in the place of iron, if aluminum has been substituted, I think that can be identified through the refinement. Am I right, sir?
Yeah. You can get the composition of how much.
How much iron is actually replaced with aluminum.
Yes.
So if I am trying with the cobalt,
yes,
can I identify it?
With X-rays, it is very difficult for cobalt and iron because of the fluorescence.
Okay.
One is that. Second is that cobalt and iron are 1 electron apart.
Yes.
So it is very difficult to distinguish between cobalt and iron.
Okay.
So with X-rays, it will be very difficult.
So how much the minimum difference should be there, sir, in terms of atomic number? So you said it is very 26 and 27, so obviously it's difficult. So like that, how many the atomic number difference? Like in case of aluminum is it's so high, so the difference is high. So
actually you can actually look into the scattering factor for aluminum, for iron and cobalt. Okay. Of course, in case of X-rays, it is well known that it is Z dependent. But if there is a difference of I think 4-5 electrons, you can have some idea about how it is working. 1 electron is too close, and iron and cobalt have another problem of fluorescence. So it is very difficult to, unless you have very good beta filter or nickel filter, it is very difficult to identify these two.
Okay. Thank you, sir. Thank you.
Sure.
Sir,
Yes, ma'am.
I have one doubt, sir. Like, if you are working, as you said, that 1 electron system could be very difficult to identify in the powder XRD. So it is valid for all the elements, or it is just for some particular, like you say, let's say example you did for cobalt and iron. If you are working for cadmium and silver, then there will be the one electron difference again.
Yeah.
So we are getting the same problem in
same
that
problem.
or not?
Yeah.
But you see, sir. You see one dominating phase in that silver won't go for hexagonal. Silver always stays in orthorhombic pattern, and cadmium always stays preferred geometry that is hexagonal or cubic pattern, cadmium sulfide especially if you're talking about. So in that case also it is not valid to identify completely.
No, in this case you have two different structures. So they had their own fingerprint in the XRD pattern, right? So that is
yes, sir.
Yeah. So when you do two-phase refinement, it is easy to distinguish between two phases. But in the same phase, if you are replacing cadmium by say silver,
okay,
so it is very difficult to see what is what.
Okay, sir. Okay, yeah, thank you.
Thank you.
So just to add to my previous question. So suppose imagine we are working with the spinel system, so which has both tetrahedral and octahedral structure. So suppose can we identify where the substitution is taking place, whether in tetrahedral or in octahedral through XRD?
Yeah, you can do that, because in case of spinels you have clear distinct peaks which are marked for tetrahedral position, which are marked for octahedral position. So those peak intensities you can track, and you can find out what is how your substitution is working, on which side it is working. So that is possible. For spinels it is possible. Yeah, for spinels it is possible.
Oh, thank you, sir. Thank you very much.
Thank you, sir.
Thank you, sir, for the talk. Sir, I just have one small question. Sir, while refining the thermal parameters, sir, it has been observed, like, particularly for oxygen, it shows a very, like, it's of the order of 20, sometimes it goes. And while for other metals, like, it is, like, 2 or 3. So, sir, is it acceptable value?
No, no, ma'am. Actually, the unit of thermal parameters is in angstrom squares. Okay.
Yes.
So just imagine 20 or 30 angstrom squares is meaningless. Your structure is not stable. So for X-rays, I think it is better not to fiddle with that unless you are very sure. It can be of the order of 1 or 2 angstrom squares. Yeah, it cannot be more too high.
Okay, sir.
For X-rays, I think you can keep it 0 and you can refine. You can still get a good pattern.
Okay,
Not
starting with 0 and then like refining.
Keep it 0. It doesn't make a difference. You can get a good fit.
Thank you, sir.
Unless you have a literature value, you can keep that value and maybe you can then refine it at the last cycle. Once you have minimized all the parameters, just to
Yes.
get a feel. So if you are working at room temperature, keeping it 0 doesn't make a difference.
Okay, sir. Thank you, sir.
Sure.
Sir, one question is there.
Yes, ma'am.
Is there any minimum value of intensity that should be there for Rietveld refinement? Like, if your X-ray intensity is not very high, can we do it? Like, what should be the minimum intensity values?
It depends upon signal to noise ratio. You should have very small signal, very small noise, a background, and very large signal. So the signal to noise ratio, if it is good, then you can do that refinement. It should not be a problem. Okay. And you can another thing to keep in mind is that you cannot have negative intensities. Okay, sometimes people subtract the background and give you the data. So make sure that you add some constant values, make it positive. Okay, shift it up so that it is positive, and then do the refinement. If your sample has a if your data file has a negative intensities, then it becomes very difficult to converge.
Okay, so we can do that like manually, so add up and something like that.
Yeah, I can show you tomorrow in one of the. It is very easy to do that in Fullprof in WinPlotter, so I can just do that.
Okay.
Without disturbing anything, without doing anything to the data, you just shift it up, make it on the Y scale.
Okay.
And you can do that. So it happens sometimes when you subtract the background from the instrument data. Actually, that time it becomes a negative. So you should not be negative. That's
okay, sir. Okay.
Good afternoon, sir.
Good afternoon.
Sir, my question is it possible to do Rietveld refinement for thin film as well?
No, sir. No. So point is that thin films are highly textured, oriented, and you have substrate contribution also. So unless you do thin films diffraction in what is called as a grazing incidence.
Yes, sir.
Grazing incidence is almost like a powder diffraction.
Yes, sir.
But otherwise, it's very difficult to do that. In epitaxial mode, it is not possible to do that.
So most of the samples are run on GIXRD, as you told me. So is it possible for that?
Yeah, you can do that. Yeah. Okay, but you have to make sure that there is no peak contribution from the substrate.
Substrate.
Then it should.
There is no dependency on intensity.
I didn't get it. Yeah.
Hello, sir.
Yes. Yes.
Sir, basically, if we have, basically, I'm working on metal organic framework type structure. So, if we not have a known structure, so how can we generate the structure at first? As you have said that without knowing the structure, we cannot do the Rietveld refinement. So how can we generate the model at first? And the second question is it mandatory to do Rietveld analysis in Fullprof software? As we generally used modeling in Material Studio or something like software. So there is an option in Rietveld analysis in that software too. So whether it is possible in that software or not?
Yeah. See, there, as I said, the Rietveld refinement method is implemented in various softwares. Fullprof is one of them. Okay, that is the first part. There are many options. You can like GSAS, Yana, and others, Retan. Maybe Material Studio also has an option of doing Rietveld analysis. So Fullprof is not the only software. You can do other softwares also. And to answer you to your first part of the question, you have to, in case you don't know the structure, so determining it from powder diffraction is very difficult. So there are certain direct methods which are available. So something called simulated annealing. You can actually search for that in on Google. There are certain in Fullprof, there are certain methods which are available called direct methods, but they are not very straightforward. It takes a lot of time and effort if you have no idea about what the structure will be, right? So you will be actually shooting in dark, working with the direct methods. So the best possible way of starting refinement is to look for an isostructural compound, for which the structure is known, or isotypic compound, for which the structure is known. So you need to have some information about the structure to start. Otherwise, you can use the direct methods, but it is not straightforward. It takes a lot of time. Yeah.
Good evening, sir.
Good evening, sir.
Sir, I am working on perovskite materials like AbO3 structure.
Okay.
In the B cation, I took two type of elements like zirconium and titanium. Okay. After completion of my refinement studies, the center cation, it shows the entire half atom, it shows one color, and another half it shows another color. I got that refinement chi-square value is nearly 3.1.
Okay.
Is it right or not? Is it possible that one atom will be converted to, the two atoms will converted to one? Is it possible?
No. It is the base, only the representation which you are seeing. Okay. So in the unit cell, when you say that you have replaced 50% of zirconium by titanium at the B side, what it means is that maybe you have say lead zirconium oxide and lead titanium oxide in 50-50%. Okay?
Yes, sir. Yes.
So 50% of your unit cell in the entire system will be lead zirconium oxide, and 50% will be lead titanium oxide.
Okay.
Okay. So basically, they are sharing the same crystallographic site.
Okay, sir.
So you statistically they are distributed. That's all. This is the way of representation.
Someone are telling it is wrong. It will show the central atom. It will show the big, and one more small atom will be shared like that. The graphical representation, it will be like that. Someone are telling.
No. So for one crystallographic site, it will generate one position. Okay.
Okay,
and then
sir.
there is a repetition of that in the lattice, right? So, so in the crystallographic in itself, you have only one crystallographic site which is possible. So you are sharing that site. So you in representation also it will be like that.
Okay, sir. Thank you.
Okay. So both will show the same site. That's all.
Okay, sir.
Yes, sir.
Sir?
Yes, sir.
What is the difference between profile fitting and Rietveld refinement, sir?
Rietveld refinement, okay, it's a method actually, and in Fullprof, using the entire profile, the entire whatever data we are collecting in the entire 2 theta range, we are using that. So we are doing the fitting. The difference between the Liebel fit and Fullprof is that in Liebel we are just using the cell parameters and space group to do the from the integrated intensities. We are trying to fit the pattern and see if the space group and lattice parameters are correct or not. In case of Fullprof, we are using the atomic model also, structural model. We are providing atomic coordinates, and we are generating the intensities on the basis of the structure factor from the model which we are using. Okay, so in case of Liebel, we are not using any structural model. In case of Fullprof, we are refining the you are using the structural model and refining that.
Okay, sir. Sir, another question is why powder diffraction method is very crucial, sir?
Yeah, see, you cannot have single crystal for every sample which you prepare, right?
Yes,
so,
sir.
So if you want to know what is the quality of your sample, if it has to be single phase or composite. If you are making a composite, it has to be composite of the composition which you are working for. So how do you identify that, whether it is correct or not? You wanted to make, say, perovskite AbO3 and it started making a A2BO4. It is quite possible. In the phase diagram, both exist. So you should know what you are studying. So having a good understanding of your sample is very important.
Okay.
And powder diffraction is one of the easiest way of doing that. First step.
Okay, thanks.
Yes.
Sir, how can we increase the signal to noise ratio? Is there any thing we can do about it?
You have to properly align your sample on the diffractometer, and your scanning time should be good enough to generate good signals. Okay. Scanning time, step size, and angular range. And of course, if you're working with a X-ray with a variable generator, you have to see that optimum power is provided, work at optimum thing, so that you generate good signal.
Okay. The scanning width should be less. It should be low.
Yeah, it depends upon the instrument. Most of the instrument it is fixed. Okay, like some Bruker instruments, they have now made it like 0.01 degree step size is possible. But most of the instruments are like 0.167, sorry, 0.0167, 0.02 degree.
Yeah, 0.2. I think we are having 0.2.
Yes, yes.
But we don't get very good signal to noise ratio. Like it is okay, but can we increase it?
Why you don't get it?
That is what I'm asking.
Yeah, how much time do you spend on getting one pattern?
One pattern, it's almost around 1 hour.
And what machine you are using?
Ricago Ultima 4, that 2 theta geometry.
Oh, okay. I think you have to work with your technician and ask him to use it at a proper voltage.
Okay, voltage.
Yeah, the generator voltage, it has to generate proper signal.
Okay, it's around 40 kilo. I think it's around that. Okay, I will ask this one.
It's a tabletop machine or it's a full-fledged machine?
Full-fledged. It is full-fledged.
Then you should generate it. Yeah.
Okay.
It has to do more with your one. Either is the generator voltage or sample. It has to be properly grinded. Okay.
Like nano powder, do we get that sample is iron cobalt only and nano powders? For that it is like that or?
Okay. See, the problem with the iron samples is that it may have a lot of fluorescence.
Okay.
And that will kill most of your signals. So unless then you have to put a filter, as a beta filter, it has to be there.
Because we get very good intensities also. It's not like that.
Yes,
but for that spinel ferrites, no.
So for mostly
for the
yes.
Nano powders.
Yeah. So I understand. I understand that. There is something called now energy dispersive detectors are there, which I mean this is off the record because you cannot change it that frequently. So they have come up with something which can cut down the fluorescence.
Okay.
So either you use the filters that will cut down the fluorescence.
We can add filters in that.
Yeah. So then you should use it for iron, nickel, cobalt, wherever you can find. It will give fluorescence. It will mess with your signals.
Okay.
Yeah, use filters. Yeah.
Thank you, sir.
Sure.
Hello, sir.
Yeah.
Sir, we are using a Rigaku Smart Lab system. Recently we bought.
Okay.
In that we have special settings like background correction, K alpha 2. All these instrumental settings are there. Should we do that, or should we left it like complete data we take and give it for refinement?
See, in refinement we can take care of K alpha and K alpha 2. So that part is fine. You can. That is fixed actually, so there's no you should not mess with that. If there is a K beta 2, then you can add a K beta 2 filter and try to remove that. Okay, in the instrument itself, not outside with that.
What about background, sir?
Background.
So they will also.
Yeah, background anyway. You are factoring it when you are doing refinement. You are giving a background function. You can working with that, so it's fine. So if your alignment is proper, you don't have to worry too much about the backgrounds. And if you are using, there's something called air to cut air scattering. They put some knife edges, something they provide. Okay, so that will take care of any. It's initially you see a hump in the diffraction pattern that can be cut down. That is probably from the air scattering. I think that can be cut down. That is unless it messes with your signal. I think you can live with that. You can just use it as a you can use it as a part of your background and work with that. It's okay. It should be okay.
Okay, sir. Thank you.
Yeah, sure. Yes.
So,
yeah.
Sometimes the baseline is started with high intensity. What is the reason, sir?
That is probably from the air scattering. So the difference or the distance from your sample to detector and the source, you have a lot of air in between that can scatter. So they provide some filters for that. Actually, something called knife edges to cut out the air background. So that will reduce your this thing. Initial upturn which you see, that can go down.
Gradually, the intensity of the baseline will decrease. Initially, it will show very high intense.
Yes, up to 10 degrees, 15 degrees it will be there. Up to 15 degrees, then it comes down. Yeah, that's good.
Oh.
That's largely from the air scattering.
Air scattering.
Yeah.
Oh, thank you.
Yeah.
Hello, sir. Good evening.
Yes, sir. Yeah.
Sir, I am working on multiple element system, and it has not any CIF file, and it has not any mother element also. So I search and match it with other system and get space group. Suppose I match it with rhenium-24 titanium, which is in alpha Mn system. So can I use these Wyckoff positions for my systems?
Yeah, if you are sure that it has formed as an alloy,
yes, sir.
then you can do that. Yeah, you should try that.
So I am choosing one possibility that all the chemical elements was sitting on the each side. So is there any problem? So I will mention that I am choosing the one possibility that all the element is sitting on each Wyckoff side. So maybe other possibility maybe exist, but this is my assumption.
Yeah, you can have more than one solution, but the point is that once you start refining, you will know how much contribution each side is making.
Okay.
Which element sits at which side, because every site and every position will have its own structure factor. Okay, so that will have its own reflection in the pattern. So once you start doing that, you will understand how much is there.
Okay.
You can try that. I mean, I don't.
Thank you, sir.
I don't see the problem in that.
Okay. Thank you, sir.
Sure.
Okay, dear participants, Sar is with us tomorrow also.
Yeah.
Because it's so far I consumed too much of
Yeah,
time.
sure.
If you have any doubts, please note down, and tomorrow you can also ask your doubts. I think you have raised some questions on the chat box. Most of these questions can be answered in refinement tomorrow, I think so. Somebody asked how to create a file. Yeah.
Yeah, we will cover all that tomorrow. We'll see that. Okay, it should not be a problem. Okay. Maybe I will start with the zip file. Yeah, you can do that.
Yes.
Okay.
Explanation, if still your problem remains, you can ask him.
Yeah, sure. And Rashid, I will try to send you some PCR files, some DAT file, and maybe a zip file. And I will try. Otherwise, tomorrow I will do that. Okay.
Okay. Fine.
Okay.
I hope any questions. No, I think we can stop it now, sir.
Yeah, we can
any
stop for
questions
today.
from your...
I will.
Yeah,
I'll take it up tomorrow.
Now.
So maybe we. Yeah, before starting tomorrow, maybe we can answer those questions and then we can start with the refinement.
Okay,
sure.
Fine. No, sir. No problem.
Thank you very much. Thank you,
sir. It was a very wonderful session. Participants also participated well. Okay.
Sure.
Thank you, sir. We will meet tomorrow. Dear participants, we will meet again.
Sure.
Bye.
Sure. Thank you. Bye.
Bye, sir. Thank you.
Thank you, ma'am. Bye. Good night.